Hey folks, welcome to Advent of Code in F Sharp, day 21 already. We're in the last stretch, home stretch. We've got a minute to go until the puzzle for today unlocks. But I quickly want to recap yesterday's puzzle. Yesterday was the image enhancement thing. And on stream, I got like 99% done, and then we're stuck. And the reason I got stuck was because the input and the example have a subtle difference, which kind of completely changed the story. Um, yeah, the problem for me was if you take a look at these rules or the algorithm, in the example, the universe does not do anything. If you look at the rule for all dark, so if you have 9 dark pixels, that translates to binary 0, so it's the first element in the algorithm. And this means all dark stays dark. And in the end, you say all light stays light. Cool. That all works for the example. And I used that assumption. Yeah, I used that assumption somewhere in my code. But if you look at my actual input, all dark lights up and all light becomes dark. So actually, in my actual input, the universe did not, or everything outside of my known little world, that did not stay like untouched. No, that flickered every generation. So I had to take that into account. I did it by explicitly modeling like the brightness or the pixel color of every pixel in the infinite universe as a single character. And then, yeah, just taking that into account when we are going to a next version or a next enhancement, and when grabbing pixels for locations we have not met yet, we take that state into account. But other than that, our solution was actually working. So I was looking for a bug that was not there. It was a bug in my thinking again, or a bug in one of my assumptions. But what's new, right? That's programming. Let's take a look at day 21. Dirac dice. Cool. There's not much to do as you slowly descend to the bottom of the ocean. Submarine Computer challenges you to a nice game of dice. This game consists of a single die, 2 pawns, and a game board with a circular track containing 10 spaces, 1 to 10 clockwise, starting space random. We have 2 players. Players take turns moving. You roll 3 times and add up the results. Okay. Then you move your pawn that many times forward around the track, moving clockwise. Oh, we're doing circular things again. Boy, I wish we had a ring in F sharp, but okay. Wrapping back to 1 after 10, yes. So if a player's on space 7 and they roll 2, 2 on 1, that's 5, it's 12, so 10, 1 and 2. Yep, makes sense. After each player moves, they increase their score by the value of the space their pawn stopped on. Makes sense, okay. The game immediately ends as a win if for the first player that reaches at least 1,000. Cool. It's a practice game, so we have a deterministic dice. Oh, interesting. We have a 100-sided die. Cool. It rolls 1, 2, 3 up to 100 in sequence, and it starts over again. Play using this die. We get some starting positions. This is how the game would go. Blah, blah, blah. We'll get there. Probably the naive thing. Probably the naive thing will burn our CPU pretty bad. But I think for part 1... what's the sum of the first 100 numbers again? It was an easy n minus n minus. Is this first plus last? What's the n thing? Oh, the length of the array. Cool. So that's 50 times 100. Yeah, that's doable. I think it's doable for part 1. Yeah, cool. Let's grab the example. I'm not even gonna bother parsing today. We just let's encode this information into a type or into a value. Let's do the same for our input. There we go. So this is the example. Let's make sure we don't mess these two up. We could do this in a tuple and stay nice and basic, but 1, 2, first, second, yeah, that could actually work. But still, let's call this. Let's build something called state. Should we? You know what? Let's go all the way. So we have a player at a position and a score. And we have game state with 2 players. And probably something for the die. Probably something for the die as well. So our initial die is... What was it? 1 to 100? Do we start at 1 or do we start at 0? 1. And it loops. Should we make an infinite die? Well, let's make an infinite die. How do you do that? Replicate a number of times? I don't know how long we'll be playing. I'll hardcode like a 10. No. Yeah, okay. And then we just collect. I think this is a... Yeah, this is a sequence of integers, and I think it loops around as well. So let's see. Let's take first 10. That should give us 1 to 10. Yes, let's grab the first 101. So that should loop around and start back at... God. Show me! Just gonna verify. Make sure we don't have any bugs in there. Yeah, so it wraps around. This is our die, our initial die. So let's just keep a sequence of lists in our state, which is the die. Sequence of integers, sorry. So this is the first deterministic die we will be using. Also not the best approach performance-wise, but I like it. I like infinite lists. Or infinite sequences. Okay, now let's put our input and our example into this state. I'm going to put my example first, because that makes more sense in my head. So that is a state. Let's write a build state or an initial state function. Position 1, position 2, and that builds a record of that game state. So that's position 1. Or starts at 0 probably. I think so. That's player 1. Let's add a player 2. At position 2, score 0, and our die is the deterministic die. Why is that not compiling? Is it compiling? It is compiling. Cool. So that is a constructor for our initial records. So example is initial at 48. Let's see whether that works. That looks okay. And our input is 8, 6. Yeah, looks okay. Cool. We parsed our input, or like made sense of the structure. We need one more thing. Now that I think about it, we need to know whose turn it is. We're gonna keep track that as a discriminated union, and there's probably better ways or more efficient ways. I think player 1 might start. In every game. Let's take a look. Player 1 goes first. Yeah. Spaces. Let's not model the spaces. We know it's 1 to 10 and it's cycles. So let's assume a fixed board, and let's not represent that in our data, but in our logic. Now we just play the game. So we roll 3 dice. Yeah, let's just do it naively and roll the actual die 3 times. Then we move forward, wrapping around 10, after 10, and then we add the current position to player score. And we do this until someone hits 1,000. Yeah, okay. Still makes sense. Let's start thinking about this, how to play a turn. So let's assume we start at the example state. Let's see whose turn it is. So that's state dot turn. So it should be player 1. It's player 1. So now player 1 has to do something. Yep. I'm just gonna do stuff until it makes sense. That's like my general approach when I don't really know what I'm doing. So it's state dot play turn state. Something like this. So if it's player 1, then we update the state, or we update the player 1 with a function call to something called play turn, where we get the entire state and the active player. And otherwise we do the same thing for player 2, and then we need to check for a winner, and I think that's 1 turn. So there we play 2, or player 2 plays. Oh no, that's not correct. We also need to update the die, not just player. Yeah, we also need to update the die. So let me roll back. If state is player 1, then we are doing player 1 things. What do we need to do? Grab 3 die results. You can do this in one operation, right? If you have like state dot die, you can do something like split add, split. Interesting, you have list dot split add, splits list into 2 lists given the index, but you don't have that for sequences. Why not? Okay, then we'll do it in 2 different steps. So roll is state.die take 3. I don't know why this is a... I don't know why you can't do this in one thing for sequences. We have it for lists. Let's reduce that to a sum. So that should be 1 plus 2 plus 3 is 6. Yeah. And this should be the die results starting at 4. Show me. Yeah. So this is a roll. We don't have to wrap around the dice rolls, right? No, we have to wrap around positions. How does that work? Do we just add the die roll to the current position and then do modulus... Modulus what? 10? So no, 10 should be a valid state. But if we go over 10, that should drop back to 1. Yeah, okay, and we need to offset this by 1. How does that work? How does that work? So we need a 1 plus what? No. Basic math is where I... It's where I give up at 6 o'clock in the morning. Come on, let's wake up, yo. It's just basic maths. We want to see something like 1 to 10, and 1 to 10, and 1 to 10. So for numbers 1 to... Nope. For numbers 1 to 10, that's okay. But for 11, we need to start doing something. Do we need to do, like, the current position minus something? Minus 10... Yeah, minus 10 times whatever. Position modulus 10? Is there a more elegant way? So assume we're at position 1. Does this work? Not at all. Oh yeah, if this is... No, position is 1. What is 1 modulus 10? It stays 1. So yeah, we subtract 10. That's not something we want to do. Does it work for larger numbers? It appears to work for larger numbers. Yeah. So it's only not working for numbers smaller than 10. That's even worse. Let's hard code that if position is smaller than 10, then just position. Otherwise, do the hacky thing. Yeah. Let's call that wrap. I don't know if wrap is the correct term, but I don't care. And let's see this in action for a couple of positions. So let's do a... Let's do a couple of wraps to see it. So 1, 2, 3, 4, 5, 6, 7, 8, 10. Yes. 1. Oh no. And then we go off the rails. Yeah, that's minus 10, minus 20. That's definitely not... It's definitely not what we want to do. How many times does 10... Is it something like this? Yes, except for the 0 case. How do we end up with this 0? So that is the 10. If we have a 10, then we are writing 10 minus... Ah. I don't feel like thinking about this part particularly. So there is a cleaner way for sure. Yeah, there's a cleaner way for sure. This is not the way to do it, but it works. And as long as this is not becoming a performance hot path, I'm not too worried. We'll cross that bridge when we need to. Oh, that was actually the correct location. This is our take a turn thing. This somehow got messed up. So we have now a roll, we have a next die. Now we just need to update the position. Yeah. Plus the roll, and that's what we wrap. This is the updated position for player 1. And now we just need to update player 1. Yeah. State with player 1 equals... Let's just update the entire record. We have, what was it? Position is the next position. Score is... yeah, this is turning out to be nasty. We'll fix this when we need to. Plus the next position. Yes, and the only thing we need to update is position score is the die, which is the next die. So if player 1, we do this, and otherwise we need to do something else for player 2. Why is this not aligning? Because our compiler is not happy with that else thing. Let's fix that. Format, please. Thank you. Otherwise, we need to do the same thing. We can just grab that die rolling. We don't need that. That's not different. This... Yeah, let's just copy paste this for a while. For player 2. So we work on player 2 in this case. We update player 2. Update player 2 score. This is... let's take a step back. So we have next position. Let's also do next score. Digging deep into the object, so that's not really a super sweet thing to do. But it works. So this is next score. That reads a bit better. The only thing I don't like about this code is the duplication, but for just 2 players, not really a problem. And the digging deep into the records. Don't really like that either. But okay. So this becomes player 2. Player 2, and we update player 2. For the rest, I think that stays. I think this might be a take turn. Oh no, we need to change one more thing, and that is who the next player is. So we have player updated, die updated. We also need to turn. So we need to toggle turns. If player 1 has taken a turn, player 2 becomes the active player, and vice versa. Now we can play a turn. Cool. Yeah, now we just play a turn until some player reaches 1,000. So let's write a function play until winner, recursive, because we will be playing a lot. If state dot, let's annotate that type so compiler can help us. At least 1,000 was what we were supposed to take a look at that. Yeah, at least 1,000. If player 1 or player 2 has that many points, we're golden. Then we're done. Otherwise, we go again. State. Did we not have a play turn? Take turn, okay. So we just take one turn and we check again. Let's try taking some turns in the example of playing until we have a winner. It didn't even verify. We have something. We have something. What do we do now? We need to count how many times we rolled the die, and we need the points of the losing player. We have the points of the losing player. Yeah, we need take into account the number of die rolls. Let's put it into the global state. Sure. Number rolls. So let's put that at 0 initially. And every time we roll, let's update that. Which is here. The duplication is spreading, or we have to duplicate a whole lot. I don't really care for Advent of Code stuff, or not even for production code, or for on-the-job code. If the duplication is like close to each other, serve its purpose as documentation, and there's only one copy paste, then who cares? Number rolls 331. That's not correct. Oh yeah, we roll 3 times every time. Because we take 3 rolls. Yeah. Yeah, let's just hard code that. Or no, I'm gonna put it close to where we actually roll. Oh, this is even better. So we roll a certain amount of times and we record that fact in our updated state. Now maybe we know everything. 745, 993. This might burn our CPU for part 1, I'm afraid, but okay. We have an end state, and then we just do score of the loser. I'm not even gonna write logic to grab that. I'm just gonna manually calculate that. Yeah, that looks correct. Let's see if this works for our input. That was actually pretty fast. Who wins? Player 1 wins. So we need this score and the number of die rolls. 747. We get a small-ish number. That might be correct. That is correct. Cool. But now, the CPU burner, probably. I'm going to copy-paste my file. Let bygones be bygones. Let's take a look-see. Now that we're warmed up, there we go. I don't feel very warmed up, so that'll be interesting. Time to play the real game. Now we got the Dirac dice. Okay, cool. Out of it falls a single 3-sided die. As you experiment with a die, you feel a little strange. Brochure explains that this is a quantum die. When you roll it, the universe splits into multiple copies. Oh, oh dear. 1 copy for each possible outcome of the die. In this case, rolling the... What is Dirac? Is that like a physics thing we should know? Paul Dirac, yeah. What did he do? Quantum mechanics. Ah. Okay. Every time we roll the die, the universe splits into all the copies for each possible outcome. You have a 3-sided die, so the universe splits into 3 versions. Oh, this reminds me of a book. What was it called? It's not Black Hole. It was something like that. Never mind. There's a lot of books on multiple parallel universe stuff. So every time we roll a die, the universe splits into 3 copies. Ooh, when we roll 3 times. The game now ends with either player score reaches at least 21. That's a poor comfort. So every player rolls 3 dice. That means that the universe splits, or the number of universes grows by a factor of 3 every roll or every turn we take. That grows fast, but okay. Those look like big numbers. Step 1. Let's make these longs. Position doesn't have to be long. Oh, no, position doesn't have to be allowed. It's the score and the number of rolls that'll start to hurt. I'm just gonna keep rolling. Keep rolling, rolling, rolling. Yeah, okay, so we have our 3-sided die that keeps rolling, or at least it rolls pretty far, not infinitely. Our score is alone. Chuk, 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 chuk. Our die are not. Positions are not. Yeah, that's enough, I think. So what has changed? Score is alone. So here we can box next position into a... What's the... How can you make a long out of a... in 64? Takes an integer, returns an N64. Yeah, okay. We take 3 rolls. Does it make sense to have a long here? Yep. I'm not even thinking about part 2. I'm just warming up my brain. Doing the things, the easy things. To accommodate for very big numbers. Okay, now I'm getting sick of doing it actually. But we're almost there, so. This should still work. Did we change anything? Yeah, we changed something. The roll, the die is now 1 to 3. Let's maybe do a quick sanity check whether or not we broke anything. 747, 6474. I think that is the same. So our die can go back to being a 3-sided die, but now every time we roll the die, we have to split into all 3 possible outcomes. So actually it doesn't make sense to have a die anymore, because we need to take all elements into account. I'm just going to say our deterministic die is, these are all the possible values. We can hardcode 1, 2, and 3 somewhere. That would be the same thing. But now let's never change this die. Let's just try every option. So that would be here. No, state.die. Let's rename that. And that means we have a 1, a 2, and a 3. So we will not be returning a single state, we will be returning a list of states. But other than that, I think it's just the same. So instead of getting a single state back, we get a collection of states. Yeah, that's actually pretty doable, I think. Or from a what we have to do functionally. I don't know if this will be a performance nightmare just yet, so let's give it a try. So we want to map every roll. Oh no, oh no, oh no. We have to do this 3 times, right? We still roll the die 3 times every turn. Yeah, I think so. Games played us before, so we have to do this 3 times. For a single player. Yeah. What changes? What changes? We have 1, 2, and 3. And we roll our die 3 times. So that's 3 combinations times 3. That's just 9 combinations of all possible die rolls in 3 turns. Can I just not hardcode all those combinations? I think so. That's maybe easier than going down a recursive route. So what do the different die rolls look like? We roll all ones. What is that? 3 times 2 times 1, 6. Is it only that much? So that's... No, it's not. Okay. This is becoming longer than I expected. So this is everything with a 1 in front, right? One, two, three, four, five, 6, 7, 8, 9. How do you calculate the number of the combinations? There's an easy way to do this, right? You could do something... What does all pairs do again? Takes 2 lists, okay. I think we can figure out all combinations by doing something like this a couple of times. So this is ones. So this is twice. There's a combinatorics thing, probably. But I don't remember, so let's just go this route. Then we have 1, 1, 1, 1, 1. Yeah, I think if we flatten this structure, we might have it. One, two, three, 1, 2, 3, 1, 2, 3, 2. That looks correct. How many do we have now? Why could I not figure out that 27? I don't know. I don't care. So these are all the possible options in our multiple universe rolls. These are all the different die rolls we can do. Yeah, let's even go a step further and let's sum them up. We don't need to know the individual die rolls. We just need to know the totals. So these are all the possible rolls we can have on the end rolls of 3 dice rolls. I think so. So we just need to map all these 27 options as a single 3 die roll thing. So it's actually this. We have 27 options of rolling a die. And if we have one of those options, we do the same thing. Oh, that's not correct. This needs to be in there as well. Ta-ta. Things are not compiling. Yeah, okay, so roll we have. Roll can go. Number of rolls is always 3 still. Cool. So what are we doing? We are taking all the options, and for every option, we are calculating the next state. That sounds correct. And now take turn returns a list or a sequence of states, not a single state. So this, let's take as an input also a sequence of states. So this works on a sequence of states as well. And now we need to do something for every state. Let's try to find a winner. So that's exactly this thing. If we have a winner, then that's not correct, right? No. So state player score equals 1,000 or it equals 1,000. Then this is the predicate. So this returns the winner. And let's just pattern match on winner. Let's not go too fancy with option module functions. If we have a winner, we're done. Otherwise, what? We do something for every state. Yeah, we do something for every state and we can collect take turns. So we flatten all possible universes into just the one. Why is this not working? Where's the error? The type game state does not match the type sequence. What? This is a state. Oh yeah, this is the thing that has to move out. So these are all the states. And we want to keep playing. Boom. Theoretically, barring any bugs, I think this is logic that could solve it. Whether or were it not a performance nightmare. Let's see how far we get for the example. Not very far. What can we do to improve upon this? Oh, no, stop. We don't need to reach 1,000. That's the problem. We only need to reach 21, right? Yeah, that'll be better. Oh, that was easy. That's not cool. Really? Do we have more possible die rolls? We don't need to do anything. Possible die rolls can go. Ooh, it's still in there? How? Okay, we just don't use it anymore. My bad. There we go. So, let's try that again. That was too fast. Yeah. Why was it this fast? Player 1 wins in... Oh no! We need to do something else here. Game is played the same as before, although to prevent things from getting too far out of hand. The game now ends when either player's score reaches at least 21. So then that game is done, but we're not looking for a single winner. We're looking for the amount of universes every player wins. Oof. That's not a very big change, right? That's not a very big change. Let's grab all the winners. So these are winners. And the ongoing are states except the winners. We can do better. We can do a partition. Can you not do a partition? Seriously? What is it with the sequence module? Okay, let's make that a list. List dot partition. A partition takes a predicate and splits your list into two lists. First one is the true collection, where the predicate is successful. Second list is the false one. So this is actually winners ongoing. So first list contains all states with a winner. Ongoing are still games being played. And then we just need to recurse on the ongoing list. If that is empty, we're done. Otherwise, yeah, we need to recurse on the ongoing ones. I'm also going to do tail recursion. So I'm gonna put in an accumulator here. The games that have already have like a winning state. I think then everything is in place. Then we just need to write our recursion a bit differently. Let's keep it as a pattern match. So match on ongoing. If we have no ongoing, we have our winners and the won games. And those are two lists, so we should list append them, not cons them. And otherwise, we played our ongoing games. So this is a single turn for all those ongoing games. And we say recursively descend with what? What are the winners? Is this correct? Why am I seeing... It's confusing me that we have like the accumulator is the same in both cases. Does that make sense? So we have a function, play until winner, that takes a list of states. First thing that function does is partition based on whether or not the state is doing something. If we have a winner, if we have no ongoing games, we're done. And done means returning all the possible winners we care about. Cool. Otherwise, we have ongoing. This pattern match reads weird to me, but it'll do its thing. Then, for every ongoing game, we know there are ongoing games. We collect all the next versions of all the parallel universes, and we recursively descend with those ongoing games while also remembering the new winners. Yeah, might work. Why is there a compiler error? Why is there a compiler error? I don't see it. Okay, there was a parenthesis missing. What's the problem here? It's a sequence, not a list. It should be a list. Yeah, okay. Everything compiles. Let's see whether or not this is better. What will this give us? A very long list of states. And then we need to partition and player 1 wins, player 2 wins. That won't work. That's longer than an integer, right? So doing a sequence.length that returns an integer. We don't need to keep track of the winners. We need to keep track of the lengths of winners. That's going to be easier. Yes. So let's keep track of a amount of games won by every player. Yes. So number wins player 1, number wins player 2. Let's do it that way. And let's update those records accordingly. Yeah, sure. So these are the games with winners. And we need to update those too. Let's just hard code current state in there. And play until winner takes a initial tally of 0, 0. Still compiles, cool, cool. Now we just need to update those two counters. Player 2 wins equals games with winners length minus the wins of player 1. Probably, maybe, off by 1. Very probable. We need the length of this thing as well. So these are the two new wins, and we just say update accordingly. So it's this thing, player 1 wins, and it's this thing, player 2 wins. Very confusing, all those player 2 wins, number things for me. I think this might be okay. And it's just the same. Let's put that. Let's put it in a variable so we don't have to duplicate this very confusing tuple. Yeah, this function doesn't feel right. I think we're mixing two things because we're doing practically the same thing in every pattern match. Anywho, this might work, except they have to be longs. Where are we assuming that they are not longs? Right here, probably. Yeah. Let's see what we need to change for this to compile. Yeah, actually, probably it wants the first thing to be a long. And then maybe type inference can work out the magic? No, it cannot. Oh, come on. Strong typing. For numbers, you can relax. I allow you some relaxation for numbers. Okay, cool. Maybe, just maybe, this works. Maybe, just maybe, it's really slow as well. That's a shame. How can we speed this up? Doing some kind of memoization, some kind of loop detection, what makes sense here? I want to see what's happening. So let's cancel. Let's print out some states. I can't believe it's taking this long. What do we have? 27. Options was something of length 27, right? Source search space grows by a factor of 27 every iteration. Yeah, that grows pretty fast. Could be that this is does not contain a bug, but it's just slow as something. Did my REPL just load things? No. My REPL has gone off and... Hello? Oh, okay. I didn't reset, I cleared my screen. That explains. I got a feeling we might be close, except for the minor detail of performance. Let's start printing out some things. Every time we play a single set of turns... Yeah, I just want to see scores for now. So let's print out scores for now. And let's print those out. Uh, yeah, we have no index or something, so I'm just gonna print out something to show you the delimiter between rounds. Yeah, it's doing stuff. It's doing stuff all right. Could we do something? Like, there's only how many spaces? Was it 10 spaces on the board? So there's like 10 times 9. There's only a limited set of possible current states, right? Could we start grouping those together? Probably. Yeah, probably we can do something in that area. Instead of having a flat list of all the possible states, we could maybe be smarter. But how could we group them? We could get out duplicates, but duplicates for the entire thing or duplicates for only the board and keep a list of scores. What shrinks the search space the most? I think we are just hitting Stack Overflow territory, something like this. The rebel just stopped. It gave up. Oh no, that's just one. That's just one turn for one of the first turns. And there we go again. Oh, we're hitting actually close to 23 now, right? I see numbers in the 20s. This might take one more generation, but this is only the small and carefully selected example, not my actual input, so might need some optimization here. Mm. Mm-mm-mm. Should we print out the states? Or should we just go on ahead and group every board, like every board location, like player 1 is here, player 2 is there. Those are just two numbers. That can be two, but it's very large search space. Yeah, it might actually work. I'm not sure on how to group. Should we just group on the positions? Should we group on positions and scores? If we group on positions, we need to keep track of a list of all the scores for that board state. That's already hard for my brain to wrap its head around. If we keep track of the entire state, that actually might work as well. If you look at how big this search space is. Yeah. So let's just... Do we need number of roles? Do not think so. Okay, let's get rid of everything we don't need. So that's just number of roles. And then just deduplicate the list of states, but the entire state. Like, let's not do anything fancy here. Or it'll be fancy, but let's not go in overkill. So let's forget about the number of roles. We don't need those for part 2. I don't think we need them, no. So basic algorithm stays the same. It's just in that major function in the end here that we want to start grouping things. Come on, brain, stick with me. This is my brain after an hour of F sharp. It's complete mush. Okay, so we do player 1 wins, player 2 wins. What changes? Instead of a single list of games, we have a single list of states. We have a list of states and occurrences, number of occurrences. So Actually, it's something like this. Let's always also make that long because we're in big number territory. Is occurrence something with 2 C's, 2 R's? This is just printing. What am I doing? Let's get rid of printing for a while. Okay, if we model our algorithm or recursive thing like this, so we don't have a flat list of states, but we have a list of different states and the number of times that state occurs in the search space. We can still partition into winners and losers. Sure. We don't care about the occurrences when we partition, that's true. So these are still the occurrences for winners and ongoing, yes. But now this thing. We split that list up into games with where player 1 has won, sure. Is that still... Yeah, for winners we can get rid of all the information, but this is not correct. No, this is not correct. So every game represents multiple, or every entry in our array here represents multiple wins. And that occurrences thing here is the number of wins. So we need to grab those and sum those. So I think that is correct for player 1. We grab all the states and occurrences where player 1 wins from that winner thing. And then we grab the number of occurrences, we sum that. Yeah, I think that's correct. And let's do exactly the same for player 2. My brain is too tired to figure out the best way to do this, so I'm gonna do literally the same thing. So these are the number of wins for 1, number of wins for 2. Next win tally is exactly this. Yes, I think that's cool. Works. But now, that was the easy part. That's the initial value. So we have the example that occurs just once. A once instead of a 0 would make more sense. But now, these are the ongoing games with their occurrences. So we say play every ongoing game. Take a turn. That's a list of states again. Yeah, okay, let's group by whatever, ID. And this is where I'm not sure whether we should group by ID or something smaller, something more fine-grained. So that's a group, and we map the group on what? On the state itself and the outer level of occurrences times the length of the group. Something like this. Roughly something like this. So it's the state and the length of the group. What's the problem here? List. list. Full. No. Okay, and it needs to be a long. Cool. That compiles. I have no idea. That was a very big step to take without any kind of validation. We have 0 tests. The only test we have is running the code and begging for a correct answer, or even begging for termination. That would be a good start. We got rid of our prints, right? Let's print the number of different states we have. That might be interesting information. So working on what? Different states, which is the states length. Yeah. Is my rebel doing stuff? Why is it stuck? Did I do the reset versus cancel again? Apparently I did. Cool. Wake up, dear rebel. There we go. Let's see. That search space is growing. Growing pretty large. Is this an improvement or have we not won anything? We have a board of 10 spots and 2 players. 10 spots, 2 players. So every player can take a spot. Can they take the same spot? Yeah. So that's what, 100 different boards. And these are already in the millions, but that's because we take the entire state and deduplicate on that. So that gets bad. If we deduplicate on the board positions and just keep track of the scores next to that, would that be a better thing to do? Yeah, probably. Then we only have 100 different states to take a look at every time instead of the millions of states. Shoot! Close, but not quite. So what would that look like? What would that look like? It would be easier if our take turn did not really, or did not only update the state, or we can keep using this, but we need to maintain our like global state a bit differently. So let's say instead of keying on game state as an entire thing, where are we doing that keying on state? Here, we're using the entire state as a key for the duplication count. What if we become a bit smarter and only key on the board positions? And instead of the number of occurrences, let's keep track of the intermediate scores. So a list of scores. Different scores, yeah. So every state multiple states can have the same layout on the board, but it could be that player 1 has arrived at that location with different die rolls, so they have a different score. So I think actually the structure stays largely the same, except that our number of occurrences should be a list of tuples containing the scores. So this state and every occurrence here is like an intermediate score for that state. Yes, so this state and the intermediate score is 0, 0. Wait, let's fall back. I'm going to commit this. This might do something correct. We haven't verified it, so it's a bit dangerous, but I'm gonna commit it. 21 with probable naive optimization entire state as the duplication key. And let's do something smarter now. Let's not keep track of the numbers, but let's keep track of all the intermediate scores. So our initial thing has 0, 0 as scores, and it's just one occurrence. So, oh yeah, this has to be a list. Oh, it's getting crazy. Yeah, it's getting crazy. Cancel, reset, give up. So this means for every state, we have a list of intermediate scores that are currently occupying that state. Yes, but it's not really the state we want, it's the board position. Oof, and there's also that turn thing. Yeah, that turn thing, that turn thing is actually pretty important. So the only thing that has to go out is the scores. Or we can take the turn out of there as well. That will shrink our search space by a factor of 2. That doesn't sound worth it. Could we do something else? Could we do memoization? That's most of the times easier than what I'm trying to achieve here. What could we memoize in theory? No. Tricky. I think we are on the right track. Just hard to get my brain around. Let's roll back. Let's take a step back. So this was maybe something that potentially could work, but our search space is still too big to do naively, even with the optimization of grouping states together. Do we group states together? Yes. Are these the only games we need to take a look at? Yes, we partition states. These are the ones we can forget all about. These are the ones that need some TLC, which we do here. Could we push this one further? The thing I was discussing, can I do it, or is my brain not up to the task? Does it need glucose first? I think it needs glucose first. How fast does this thing grow? So first we have just the one state, which is the initial state, yeah? And then we do 27 different universes, and apparently there's only 7 different ones. That's actually pretty sweet, optimization-wise, but it's not enough, really. Yeah, it's the score thing, probably. Stop. It's still running in the background. So that's a factor of 7, 7, 7, 7. It grows by a factor of 7 every time. But the problem is it grows. Yes. If we partition or do the grouping on something smaller, something really deterministic, it's like maybe just a player state or just a position, the position and the current turn, excluding the scores, then our search space is like 10 times 10 times 2, that's 200. So that would mean we would cap out at 200 different states. This is starting to sound more and more like a good idea. Like a trademark good idea. The only way out of this combinatoric explosion. Yeah, that's probably a smarter thing to do. Just thinking, should I do this now on a empty brain, or should I get some breakfast first and figure it out later? Yeah, I think I'm going to wreck my solution, evict the score thing from this record, and just return that explicitly. So we have like the next board position, which is position player 1, position player 2, and the current player's turn. And then have just a list of possible scores. Oh no, this is a list already. Yeah, it's something like that. I want to migrate towards something like that. And then this gets even trickier. Oh boy, this is an unmaintainable mess of a code base already. But I think the concept or the idea still stands. We'll try that in an hour or something, but first I'm going to grab some breakfast. Thanks for watching. You have been watching Advent of Code in F Sharp. This was day 21. Part 1 was doable. Part 2 also, but it's a tricky performance optimization thing. Have a nice day, and I'll see you next time. Bye-bye.